behind here on schedule. So we had left off talking about dictionaries. I'm gonna vamp for a few minutes just so that we were talking about dictionaries, and as a reminder, where we were. We're about to do a demo, a live demo. So just bear with us for a second. Let's make sure that most folks are here. I didn't launch the stream early today. Just got busy. So there are still two groups that haven't talked to the TA about who the group leader is and who made their repository. So if you are groups 9 or 11, 9 and 11, you guys are not working in the project. Not sure what to tell you. If you don't know what group you're in, please email the TA to figure out what group you are, or check your email because he's already emailed. Okay. So what we're going to do, we are going to start with the demo of the dictionary. Let's just go back. Let's remind everybody the point of the dictionary. So here I have a dictionary of audio is kind of yeah, that's because it's a headset. It's not there. Let's do that. Okay. All right, quick recap of everything I just said. Groups 9 and 11 haven't checked in with the TA, so do that. If you don't know what group you're in, check your email. If you have no email from the TA, email the TA. Okay, so the whole point of a dictionary is it's a different way of storing collections of data, our abstract data type. All right, so with a dictionary, it's not addressed via index, it's indexed via a key. So here we have kind of the opposite of what we might normally think of. An integer is actually our data, and the string is going to be, for lack of a better word, the index. Certainly it's what we use in the indexer. So here's how we might use a dictionary. We can add things to a dictionary, but we add them based on a key and a value. And the method signature for this is going to be whatever the first type is and then whatever the second type is. So when we add Ivan 4, what we're really saying is there is some index called Ivan whose value is 4. And Peter is 6. Maria is 6. George is 5. The data can be duplicated. So we have a data of 6 here and there. For Maria and Peter, and that doesn't matter. The only thing we can't do is have a key that is a duplicate. That would be a problem, which is why it's commented out. Once we have information in our dictionary, we can access it using the square brackets, our indexer operation, and we pass in a key. So Peter will give us 6. Student marks get an indexer, which returns the second templated type, int. Okay. And then there's a few other pieces here. So let's run this, make sure that this shows up correctly here. Let's compare our output with what's going on. So the first thing we see is that Peter's mark is 6. Okay, the value that student mark sub Peter returns is 6. Furthermore, we can actually check to see if Peter is in the dictionary. Then we say that with the contains key method. Once we remove something, and we remove it based on the key, it says removed, and then we can check, does it contain the key, and we get false. Further, we can check on Ivan still, Ivan, and Maria, and so forth. However, here's sort of the interesting piece here. This is how we iterate over a dictionary. And I said last class, when you iterate over something, we saw when you enumerate, it actually returns a key value pair. So technically, this student mark, it's actually the IntelliSense is smart enough to show us that is actually a key value pair of a string and an int. However, that's a little long in the tooth, so C#, being fairly intelligent, has a catch-all var keyword. Var just means whatever the data type is supposed to be. Infer from it what it's supposed to be. It's kind of like a void reference, but let's not go there. So when we iterate over student marks, which is a dictionary of string, int, key value pairs, student mark is itself a single key value pair. And student mark, you can see, has two properties, key and value. Other than that, it's just a placeholder. It doesn't really do anything, it just stores some data. There's no special methods associated with it beyond what you would find in object, in the C# object. So yeah, we could either say key value pair here or var. But a couple of things we cannot do. So let's go and get rid of that. First thing we can't do is we cannot add something whose key already exists in the dictionary. This is going to differ from sets a little bit, but if I run this, I actually get a runtime error. And let's just look at that. Item with the same key has already been added. It's part of the dictionary's add method. Okay, and so you get an argument exception. It already exists. So a dictionary cannot have multiple instances of the same key inside of it. Likewise, if I tried to print, so I'll do exactly the same thing I did here. Peter mark. Peter is removed. So I've definitely removed Peter from the dictionary, but I'm going to try and access it anyway. Okay, so let's do that, and let's run that right there. So Peter has been removed, Peter is not in the hash table, and now we get a different kind of exception, a key not found exception, which is exactly what you would expect. But one thing I can do, student marks sub Peter, just making a note to myself for next time. So now we've actually said Peter. Now, we know that right at this line, the student marks dictionary does not contain the key Peter. Okay, so we're going to run this. And it did not crash. The reason it didn't crash, here it says, okay, it's not in the hash table, it's false. However, the exception is only going to occur on reads, not on writes. So here, we're doing a read. So if you read from something that doesn't exist, it throws an exception. If you write to something that doesn't exist, it automatically adds it into the dictionary. So two things. All right. And I'll keep this off here. Okay. So things about this demo, you can iterate over things. You can write even if something is in there. Okay. You can also write even if the entire key doesn't exist. Okay. So that's basic dictionaries. Now, why might you use dictionaries more than just keeping track of data? Well, this, or a variant of this problem, okay, counting words in a particular string of text, is a tried and true programming problem. And dictionaries like this, like I said, I think last class, if you Google or DuckDuckGo or whatever search engine you want, but if you look up coding interview questions, get failed, final BC, SQLite database. Interesting. I'll have to look at that. Text the TA with GitHub errors like that. So this is a problem that on its surface is very easy for us to do. Okay, count the number of words in a particular string. So if I wanted to know the number of the words welcome, okay, I could start, I'd look at this word, that's one, welcome, going over each word. There's only one word, welcome. What about the word in? How many word ins are there? Well, I see a word in there, two, and then that's total of two. Programmatically, if we had to do this, this could become quite difficult because we don't know what words we're going to find. With a dictionary, we don't have to care, okay? All we're going to do, let's look at count words. Count words is a method, or it was a method. Did I delete? I deleted count words. Okay, count words takes in an input string and some dictionary, okay? Now, I want to point out that this dictionary is a generic pointer to any kind of dictionary. This iDictionary can point to either the dictionary object or the sorted dictionary object. And just to demonstrate the difference between them, okay? The difference between both. All right, so what does count words do? It says, okay, first off, split the entire string based on spaces or commas, get rid of the punctuation, and just give me an array, a immutable array of words. Then iterate over the words. So this right here is big O of n. It's going to operate once per word. And the operation is if the word count dictionary contains the word, add 1 to its count. Otherwise, set its count equal to 1. All right. So what's this really doing? Let's step through this one line at a time. So first thing we're going to do is we're going to take this very long text. Welcome to C# course. This is where you'll learn to use C# and how to use data structures. Fine. We split it up into an array. So there's 24 words in this array. You can look at them down here. Welcome to our C# course, blah, 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 and use data structures. Now we're going to iterate over each word. So each time we go through the loop, we're looking at one word. In this case, the word is welcome. Now, word count is a dictionary. There's nothing in it. Let me put a watch window up. Put that here. With word count, words count. Okay, so there's nothing in it. But the first time through the loop, what do? We're going to say, okay, assume that the count is 1. And then we're going to check to see if word count contains welcome, which it does not. So what we're going to do here is we're going to write to the key welcome, and we're going to put 1 in as the data. Now, we saw from the previous demo, even though it doesn't exist currently, we can do that. It adds it as a side effect. So now word count does have an entry for welcome with an item 1. When we come back up, how to put a watch window. So watch windows are typically always there. It's usually in the bottom left-hand side, along with autos and locals. What I did, since I wanted to keep track of the locals, I just clicked and drag it. Now, as soon as you click, it doesn't show up, but I've got a window that I'm dragging around the screen, and then I can drop it into another pane. Now, if you don't have a watch window, you can go up to debug. Ooh, you cannot see that. If you go to debug windows, one of them is the watch window. There's also a keyboard shortcut for it. Control-Alt-W and then 1, 2, 3, or 4 to get multiple watch windows. So this is watch window 1. I think if I close it and then do Control-Alt-W1, do I get it back? Nope. Control-Alt. Oh, yeah, I did get it back, but I got it back in the original pane, so put it there. Okay, so the next word is 2, and 2 is not in the dictionary, so we're going to put it in as word 1. Can I keep this open? That would be nice if I could keep that open. And also, hold on, let me actually get into fonts and colors. Display items, watch windows. Watch windows, size 16. Until I restart the application. All right, for the sake of readability, I'm just going to restart Visual Studio here for a second. Bear with me. I want you to be able to see what's going on down in the watch window. So, hash table demos. Counting words. Open it up. Run it. Put a breakpoint on it. Run it. Okay. So here we go through now. Now we can actually see things a little bit better. So our watch window, I want to watch words count. Keep that open. Is that a little bit easier to read? I hope so. So our second word is to. So far, we're actually not really getting that much information. We're just adding each word to the dictionary. The third word is our, so still nothing interesting here. I'm going to put a breakpoint right here. Let's go through. We actually get through several words. Welcome to our C# course. In this, now the word is course again. So when you do a contains key for course, it returned true. So now what we're going to do is we're going to use the get indexer, which is going to return 1 because there it is. It's element 4 in this order dictionary. And we're going to add 1, store that in count. So count is now 2. Now we can go one step further. When we assign count back to word, the only thing that's going to change is course. Okay. Now, we could have written something that would have done some sort of a linear search, find things, keep a pointer to it or a reference to it, then write back to that particular location. But a dictionary does it in constant time. Okay, so as we go along, you is not a word in the dictionary, so it gets a brand new count. Let's continue on. The next time, the word that is duplicated is the word to. So the word to already exists. It was the second word. So when we run this again, it's incremented just the word to. All right. So when we get down to the bottom here, count words. Actually, I want to get to here. Let's run through all of this. So now we have word count, and we can either print it out, which is what this does, or look in our debug window. So the words to were used 3 times, course was twice, how was twice, everything else was once. So total, there were 18 unique words in this sentence out of 24 words. Okay. So the next thing, and the reason that we have count words twice in this dictionary example, is because we're using 2 different underlying types, one dictionary, one called sorted dictionary. So when we use a dictionary and we print it out by iterating over the key value pairs, this is the important thing. I want to go to here and I want to look at the order. The order is the order in which they were added. Welcome to our C# course. In this course, which is, oh, you can't see that because it needs to be debugged. Okay. Let's shrink that there and then make this much bigger over here. Okay. So here, can I do it like this? Okay, there we go. So it's the order in which they were added. There's no implied order here. It's just as they arrived, that's the order they were stored in. So it's an unordered dictionary, meaning there's no logic behind how it was printed. We just iterated over it and we got it in exactly the same order that the words occurred. Welcome is first, structures is last. Okay. So that is going to be contrasted now with a sorted dictionary. Get rid of some of these items here. So I'm going to run this. It will have already printed out everything we needed to know about a where did it go? Don't have my thing open yet. But when I look at word count the second time, okay, we're going to do exactly the same thing, but instead of a dictionary, we're going to use a sorted dictionary. Sorted dictionary, same type of setup. It's strings are the keys, ints are the data. And we're going to count the words in the same text. So this method signature can take either type because both sorted dictionary and dictionary as a class, they implement the iDictionary interface. So we could never instantiate something that is an interface, but we can create a reference pointer to something that inherits from that, or rather implements it. All right, so here we go. Let's go inside of count words now. So overall, we're going to see fairly similar behavior. It's going to get the first word. It's going to set the count equal to 1, go along. Every once in a while, it will find another word. In this case, the word is course. So course gets updated to 2. But already we can see that there's a bit of a difference. Look at the ordering that it's presenting things to us in. It's no longer based on the order in which they arrived. The order is now alphabetical. Okay, and when we so let's go all the way to the printing. When we print this, roll this up. Why can I not see the debug window? It's interesting. Put that back. I want this. Here, oh geez, that's completely unnecessary to be that large. There we go. So reminder, this is how we printed out our dictionary object. Dictionary object was in the order in which elements arrived. Sorted dictionary certainly looks to be what? Alphabetical. And A, B, C, D, H, I, L, O, P, S, T, U, W. And interestingly enough, it's case insensitive alphabetical. So how does a sorted dictionary do that? Well, a sorted dictionary relies on the fact that the key has a comparison method. All right. If we look at, let's stop debugging. If we look at the sorted dictionary, go to definition. It relies on the fact that key collection sorted enumerator. Actually, this is not the best way to show this to you. Let me actually do it a slightly different way. Let me go back over here. So we had actually talked about sorted dictionaries. Hash tables, the dictionary, we did that. Did the live demo with counting words. Oh. Where are we? I want the slide that just goes over. There's the background on hashing functions. Hash tables, add, find. Dictionary. Add, remove keys, values. Oh, here we go. Okay. So pop that open. So the sorted dictionary has some extra logic, and it really just relies on the underlying data structure of the key type. All right. They're ordered by the key. And when you traverse, that's what you usually call it when you're going through a tree, when you traverse the dictionary, it gives them in increasing order. So it's a little different from a dictionary, where the dictionary is a constant time operation. It just takes the time to hash the key, and then it can get there in constant time. A sorted dictionary is worse performance. It's log, specifically log base 2 of n. So we call it log n. And that's because for every doubling of the size of the dictionary, it increases the number of operations by 1. Because log base 2. So if you need the elements sorted, for example, words that need to be sorted, you can use the sorted dictionary. Otherwise, you can use dictionary because it does have that better performance, the constant time add, find, and delete. But log base 2, not terrible. So there's that sorted dictionary. The code looks exactly the same because it's not using any of the special features of a sorted dictionary. It's just getting them as a side effect. All right. So how do you do that? If you're making your own class that you want to put into a sorted dictionary, you have to be able to compare your keys. All right. So if you're making a custom, so a room that goes into a dictionary, for example, as a key, not as a value. All right. We have to implement object.equals. So object.equals is a method that every object has. All right. But it relies on the fact that that exists. So when you do a dictionary, it's just equals and get hash code. But when you're doing a sorted dictionary, key must implement the comparable interface. So things like ints and longs and floats and strings, they already implement equals, they implement comparable, and they implement get hash code. But when you have to, when you have to write your own class, you have to implement that comparable interface. So let's just for a moment look at what that might entail. Go back to Visual Studio. Let me just briefly open up one of our recent projects, Quadratic. In Quadratic, we implement a complex class, okay? Now we can choose to implement the comparable to other complex numbers, and that's how you read this. This is, you can compare one complex number to another complex number. And it immediately starts yelling at me because I haven't done that. I haven't implemented those methods. So there's a couple of things we can do. And the easiest thing is just say, go ahead and implement that interface. If you right click on this when it's thing, you can have a quick action. And that quick action actually automatically generates this method stub, compare to complex. So we have to decide how to compare two complex numbers to each other. So the question is, how do you compare a complex number? For my purposes, I'm just going to say, all right, a complex number is less than another if its magnitude is less than. All right, so if it's closer to the origin. Now, what geometric figure can you create where everything is equidistant from the origin? Because everything that's on the boundary of that geometric figure would be equal to one another. Yeah, a circle. So if the magnitude of the complex number, what happened? Complex number is equal, what do we want to say? If it's equal, compare its theta. So if it's at 0 degrees, that would be considered less than if it was at 180 degrees. Okay. So how do we compare that? So the thing is, compare to has a very specific return type. All right. When you have compare to, what that really means is you return less than -1, or sorry, less than 0 if A is less than B. You return 0 if A is equal to B. And you return greater than 0 if A is greater than B. All right. So we've got to do this in a couple of steps. First step is the easiest step. If this dot real equals other dot real, and this dot imaginary equals other dot imaginary, return 0. Okay. Now, calculating the magnitude, I'm actually going to take a moment and augment this class ever so slightly, because it would be pretty simple to just write a method to calculate the magnitude. So we're going to make a read-only property. What is the magnitude of this number? That's going to be what? Pythagoras, right? The square root of, we'll do it the long way with pow. So that's going to be real, comma 2 plus math.pow imaginary, comma 2. That's the magnitude. And while we're up here, well, we've written magnitude, so we can now write it's not quite true, is it? So that equals case, there's a few other things we need to deal with here. So that takes care of the equals case. Let's write the next case. If this dot magnitude is less than other dot magnitude, actually, do this, return okay. Oh. I don't like that at all. All right, we'll just return -1. Okay, so that's less than. So if this magnitude is less than the other magnitude, we've got that. I'm actually going to get rid of this. I don't like the way I've tested for equality there. So if the magnitude is less, we're good. If the magnitude is greater than magnitude, we can return +1. So the remainder now is actually, why is it yelling at me? Not all code paths return a value. So now, if we've made it to this point, we know that the magnitude must be the same. Right? So the magnitudes are equal. And the only way, I actually want to go back and put that back. If this dot real, yeah, I like that back there. Right? Other dot real, and this dot imaginary equals other dot imaginary. Sorry, all right. Return 0. All right, fine. Wouldn't it be better to use else if? No. Here's, well, matter of opinion. But I'm going to say no, because here's why. If I used else if, that's perfectly reasonable. Okay? This will work. However, you're not, okay, so you're under the impression you're going to eliminate wasted comparisons, but you're not. Whether I put an else here or not, it's either going to return or it's going to skip down, which is the same functionality you get by saying else if. So this is preferred. There's no wasted comparison here. It's just going to short circuit evaluate. So if it tests true, it's going to return and skip over everything else anyway. All right. Why is it yelling at me? If I have lost a semicolon somewhere. Does anybody see it? Oh, there's a 1. Get out of there. Okay. So the only piece left now is if the magnitudes are equal, we have to compare their phase, their theta. So rather than writing some complicated math, let's actually just define their phase. How do you calculate the phase of an imaginary number? Well, that's the angle between the opposite and the adjacent, right? So what is that? Math dot arctan opposite. So what is the opposite? Imaginary, yep. And the real. So there you go, arctan of imaginary versus real. That's going to give us our phase. Probably in radians, but it doesn't really matter because we're just comparing them. So if the magnitudes are equal, I'm going to return this dot phase minus other dot phase. Can't do that, can I? What I can do math.sign. Math.sign. Yeah, I like that. So sign is a method. Go to definition. Oh, no comments? Can I, maybe it's for one of them? No, none of them have a... I'm disappointed. Oh, there it is, okay. Returns the sign of the specified angle. Oh, that's for sin, not for sign. Alphabetically, that doesn't make a whole lot of sense. All it's going to return, let me briefly just pull up the help here for you. Oh, you can't see that. That's actually gonna, all right. So the spoiler is that sine returns -1 if the value is less than 0, 0 if the value is 0, and 1 if the value is greater than 0, which is all we want our program to do anyway. So that's just going to return the sign of these two things subtracted. So if other.phase is larger, we're going to end up with a negative number. And math.sign will return -1. Okay? In fact, yeah, I think we're pretty good here. We could clean this up a little bit, actually, by testing to see if the magnitudes are equal or if they are not equal. But this is pretty good. So this will return 0. This will return -1 if the magnitude is less than -1. This will return greater than 1. In fact, we could use math.sign twice, depending on if the two things were equal. So I like that. So once we've done this, we've got this complex class, real and imaginary. We gave ourselves some helpful methods here for finding the magnitude and the phase. Okay. We've now implemented this method. This method is the only thing that is required of the eye-comparable complex method. Interface. The eye-comparable interface. At this point, we can now create, if we wish, a dictionary of complex string types and it's yelling at me because I haven't included system collection generic. So now it should be fine. Dictionary complex string. Okay, that's fine. But what we can also do now is create a sorted dictionary of complex numbers. All right, both of those are legal. And the thing that makes it legal is that we've put this here. If I were to comment this out, even though I still actually have the method here, all right, the method is there. Save both of these. Should give me a build error. Build. Succeeded. Was it smart enough to see that it actually did implement this? Or is this going to give me a exception? No. I'm surprised. Sorted dictionary relies on the fact that complex implements eye comparable. Interesting. Okay. All right. So that was a longer version of this. Here's what you might need to implement just for a dictionary of complex objects. Oh, you can't see that. Go here. All right. So for a dictionary, for a sorted dictionary, you need to do eye comparable. For a dictionary, you have to say get hash code. All right. For get hash code, there's lots of different ways. This is what I was hinting at earlier. Okay. Here's how they chose to implement get hash code. They took X, shifted it up by 16 bits, and twiddled it with some exclusive ORs of Y. And that's all very clever. Okay. But if we return to our project, I know you can't see this. Hang on. Yeah, save all the changes. Fine. Go to Visual Studio. Oh, no, I shouldn't have changed projects. I should have stayed with quadratic. If we wanted to override, because we would have to override because it's object, so public override get hash code. Okay. There are actually where is that method? Stand by. That method is in hash code, and hash code is in the one more time here. This dot real dot get hash code dot combine. That is what it is called. Hash code is in the system namespace. Oh, but is it in the .NET Core? Hash code, system.hashcode. Yeah, that's fine. Not a hash set, hash code. Oh, but am I in .NET Core 2.0 here? I might be. But it is there. Struct hash code. Having some difficult. Oh, because there's already some errors here, probably. So I can say real.getHashCode, and that will get, interesting. What that should have gotten was a hash code structure, but it's just getting an int. Then there is a method. Let me pull this up for a second here. At the risk of doing that. So there's a hash code structure, and then you can actually take and combine two hash codes. So this will be an implementation detail for whatever .NET framework you're using. Okay. But you can say combine, and up to 8 things if you want. Okay. So I'm not sure what I am missing here and why hash code is not showing up. I thought that it was .NET Core 2.0. No, .NET Core 2.0. Oh, so it's okay. I would have to compile this under 3.1. So let me see if I can just quickly change the project to do that. Properties. Go back to Visual Studio. Let's go. Oh, I don't even have anything over 2.0 in my computer. I would have to go and install 3.0. For your final project, while we're on the subject of .NET frameworks, you can use whatever version of the .NET framework you want. So if you want to use 3.1 or 3.2 or whatever the latest is, what was the latest? The latest .NET Core is 3.1. The latest .NET Standard is 2.1. Sorry, the .NET Framework is 4.8. So .NET Core is cross-compatible. You can have it on Linux and Windows. The .NET Framework, I think, is just Windows. I might be wrong there, but everything you've done in class, I have automatically set to be .NET Core 2.0. All right, so I cannot actually do this. I'm going to return just return int of real. Oh, just return magnitude. You can't go above 3.1 if you want me to be able to run your code. Oh, yeah. For the final project, do whatever Tim says. That should give you something nice and interesting. And parse it. Okay, moving along. I got a little distracted there. That is it for that. When we come back on Monday, we'll talk about sets. All right. And just as a preview of coming attractions, the last day of classes is what, the first? The first. So I think we're gonna have project presentations on the 27th, the 29th, and the 1st. I think it's the last 3 days of class. We may have to go one day sooner to that, being the 24th. Okay, but that's how much time we have left. So we're almost through. All right. Again, groups 9 and 11. You have not responded with who your group leader is, and that doesn't bode well for you for your project. So please get that information to Tim. Get those repos generated. All right. That is it. I will see you all on Monday. I hope you have a safe weekend. Now I've got to actually turn this off. How do I turn this off? Ah, the wonders of technology. Oh, did I close my YouTube page? No, there it is. All right. Bye, everybody.